In this video, we're going to talk about inferences, so we're going to do confidence intervals as well as hypothesis testing for a sample mean. In the previous chapter, we had talked about doing sample proportions. Now we're going to look at the mean, and for the mean, the distribution we're going to use is not the normal distribution, but the t-distribution. And when you have a large sample, the t-distribution starts to approximate the normal distribution. This is our overview slide, which we'll spend about 5 minutes going over before going over each of these topics in more detail and with more examples. In this video, we are going to talk about modeling the sample mean x bar with the normal distribution and the t-distribution. The techniques we'll be using are totally analogous to modeling the sample proportion p hat with the normal distribution that we did in the previous chapter. The t-distribution just tends to be more useful than the normal distribution with the sample mean. We start by reviewing when the sampling distribution, the t-distribution or the normal distribution, is appropriate for the sample mean. And we come back and we review the central limit theorem for the sample mean. So when we collect a sufficiently large sample of n independent observations from the population with mean mu and standard deviation sigma, then the sampling distribution of x bar, that's the sample mean, will be nearly normal, with the sampling distribution x bar equal to the mean of the population, the real population mean, and the standard error will be equal to sigma, our real population standard deviation, divided by square root of n. So the two conditions we had is that we wanted a sufficiently large sample and independent observation. So independence, much like our previous chapter, the most common way to satisfy this condition is when the sample is a simple random sample from the population. If the data comes from a random process analogous to rolling a dice, this would also satisfy the independence condition. For normality, or the sample, sufficiently large sample of n, if the sample size is less than 30, we also require the sample observations come from a normally distributed population. We can relax this condition more and more for larger and larger sample sizes, and when n is greater than or equal to 30, then all we check for is no particular extreme outliers. As I mentioned, instead of the normal distribution, we will be using the t-distribution. So we'll take a look at this distribution. The standard error is dependent on the population standard deviation. However, we rarely know the population standard deviation. Instead, we must estimate it based on the sample standard deviation. Because this estimate itself is imperfect, if we have a small sample, we use the t-distribution to fix this problem, the t-distribution rather than the normal distribution. So the degrees of freedom for the t-distribution is equal to n minus 1. The larger the degrees of freedom, in other words, the larger the sample size, the more closely the distribution approximates the normal model. We will do confidence intervals then for the sample mean. So finding a t-confidence interval for the mean based on the sample of independent and nearly normal observations, and confidence interval for the population mean is, this is our x bar, our sample mean, plus or minus our t star of degrees of freedom. This is essentially our test statistic divided by our standard error, which is sigma over square root of n, but again, we're estimating sigma with our sample standard deviation divided by square root of n. And then we'll also do hypothesis testing based on one sample. Once it's determined that a one-mean hypothesis test is the correct procedure, and by determined, that means we have satisfied our sufficiently large sample and we have independent observations, then we can do hypothesis testing. We prepare, we identify the parameter of interest, we list the hypothesis, identify the significance level, identify our x bar, our standard deviation, our sample size. We verify conditions to ensure x bar is normal using our central limit theorem. We calculate if the conditions hold, we compute the standard error, the t-score, which is the same as the z-score, but now we're using the t-distribution and p-value. Also, of course, we're using this definition of the standard error. And then finally, we evaluate the hypothesis and provide a conclusion. So this wraps up our overview. So we'll come back over here to the top and take a closer look at each topic. So again, we're working on modeling the sample mean, x bar, with the normal distribution and the t-distribution. Again, our techniques are similar to modeling the sample proportion, p hat, which we had done in the previous chapter with the normal distribution. It just happens, though, with the mean, that the t-distribution tends to be more useful. The first thing we need to do is to find if it's appropriate to model these things with the t-distribution. And we do that by looking at the central limit theorem for the sample mean. The central limit theorem for the sample mean says, when we collect a sufficiently large sample of n independent observations from the population, when the population has mean mu and standard deviation sigma, then the sampling distribution of x bar will be nearly normal, with the mean equal to the population mean and the standard error equal to the standard deviation of the population divided by square root of n. So here, our central limit theorem again has two conditions. One, a sufficiently large sample of n, and we need independent observations, n independent observations. So for independence, the most common way to satisfy this condition is when the sample is a simple random sample from the population. If the data comes from a random process analogous to rolling a die, this would also satisfy the independence condition. And the second one, normality, actually comes from a sufficiently large sample of n. When the sample size is small, so when n is less than 30, we require the sample observations to come from a normally distributed population. So for example, maybe heights, because heights is a normal distributed thing. We can relax this condition more and more for larger and larger sample sizes. For n greater than 30, then all we need to show is that there are no particularly extreme outliers. And generally, if you remember from our, 87, 95, 99.7% rule, extreme outliers would be something like 3 standard deviations or more, since 99.7% of our data lie within 3 standard deviations. One other note, the standard error is dependent on the population standard deviation. You can look at this formula for standard error. However, we rarely know the population standard deviation. The whole point is we're taking a sample because the population, it's unrealistic to sample the whole population. So we must estimate it because this estimate itself is imperfect, and we're going to use the sample standard deviation as our estimate. But because the estimate is imperfect, we use a new distribution, the t-distribution, to fix this problem. So our example of these conditions, consider the following 2 plots that come from a simple random samples from different populations. So here we have a sample with n equals 15, and this is our histogram, our distribution of our sample data. Here we have a sample size of n equals 50, and this is what our histogram of our sample data looks like. Generally, you need to be told how this sample was taken, and we are told that it's a simple random sample. So in this case, independence, the condition has been satisfied. Now we need to look at normality. We say when n is less than 30, that's this case here. We need a normally distributed population. So if I look at this, sort of maybe normalish. And when I look at this graph here, this is n is greater than 30, we need no extreme outliers. And actually here, all of our data is kind of bunched together. There's nothing outlying. So this definitely is normal. Here, as I said, it's kind of, but also one thing about this data, there is no extreme outliers. It is true that there's a gap in the data, but that's not the same as having an outlier. That is like some single observation kind of off on its own. So for normality, the graph with n equals 15, there's no outliers. Normality is somewhat met. The graph with n equals 50, there's one, oh wow, I had forgotten about this observation over here on the very far right. So it fails the normality test. I totally didn't see that. This one actually fails the normality test. Okay, now that we kind of are familiar with how to check the independence or normality, let's take a look at the t-distribution. So first, the standard error is dependent on the population standard deviation. However, we rarely know the population standard deviation. The whole point of sampling is we can't sample the entire population. So we must estimate it based on the sample standard deviation. Because this estimate itself is imperfect, we have a small sample. We use the t-distribution to fix this problem. And the degrees of freedom for the t-distribution is equal to n minus 1. The larger the degrees of freedom, over here, since degrees of freedom is n minus 1, that means the larger n is, the larger our sample size, the more closely the distribution approximates the normal curve. So I'll paste a picture of different degrees of freedom for the t-distribution. You can see it looks very much like the normal curve. It has that bell shape over here, but its tails are thicker than the normal distributions, which means observations are more likely to fall beyond 2 standard deviations from the mean than under the normal distribution. So here you can see it doesn't taper down quite as fast until you get to this normal curve is this the darker outline here, which tapers down to 0, it looks like. The extra thick tails of the t-distribution are exactly the correction needed to resolve the problem of using sample standard deviation in place of the population standard deviation. And again, looking at this, you can see when degrees of freedom is equal to 1, that's this lightest curve here. And as we increase, degrees of freedom equals 4 over here, we start to look more and more normal. And hopefully, I guess it sort of goes without saying, but I'm going to say it explicitly. Just like there are many normal curves, and the different normal curves are parameterized by your mean and your standard deviation, there's also many different chi-squared curves, and the different chi-square curves are parameterized by degrees of freedom. There are many t-distributions here, right? We have 1, 2, 3, 4 distributions, and they are parameterized by your degrees of freedom. As degrees of freedom goes up, it becomes more and more normal. And then last point, the t-distribution is always centered at 0 and has a single parameter, degrees of freedom. The degrees of freedom describes the precise form of the bell-shaped distribution. In other words, it's the one parameter you need to precisely pick out which t-distribution you're looking at. Next, we're going to practice using our table for the t-distribution to find areas under the curve. Our first example is we're given our degrees of freedom is 18, and we want the area associated at a t-test statistic of minus 2.10. So that's where we are. Standard errors away from the mean is minus 2.10. So first we're going to look at the degrees of freedom equals 18, which we have on our table. Looking down, degrees of freedom equals 18. That's this row over here. We see our test statistic, 2.10. And here we have either the one tail, which is less than, or because it's symmetric, greater than, or the two tails. But now we want just the one tail. We're not concerned about positive 2.10. So looking at one tail, it says that the area under the curve of one tail is 0.25 or 2.5%. Our next example, we're given that our degrees of freedom is equal to 20. So we're going to look at this line over here, and we want the area, one tail area, that's greater than our standard error of 1.65. So we're going to look at our table for our test statistic of 1.65, which we don't have listed on our table, but we can see it's going to be somewhere, 1.65 is between 1.33 and 1.72. So the area associated with that for one tail is over here. It's going to be associated with somewhere between 5% and 10%, or 0.05 and 0.1. So the area is between 0.05 and 0.1, or 5 and 10%. And then our next example, we have degrees of freedom is equal to 2, so we're looking at degrees of freedom equals to 2. We're looking at this line over here. And our test statistic is the area above and below 3 standard errors. So below 3 standard errors and above 3 standard errors. So we're going to look up for 3 standard errors, and I kind of crossed out some stuff, so let me get rid of this line. But we're somewhere over here in about 2.92 and 4.30. So we don't have a 3, but we're between these two numbers. Let's use 2.92 because that's That's really close to 2.3. And we see the area then, now because we want the area above and below, we're going to use the two tails line. So that's 10% or 0.1. So our area is 0.1, 10%. And finally, we have the question, what proportion of the t distribution with 19 degrees of freedom falls above the 1.79 units? So let's look from the table. Let's see, circled in yellow, that was our degrees of freedom is equal to 19. So we're on this line. And a negative 1.79 units. I guess we had done this. No, we haven't. Okay. 1.79, it's somewhere over here. This is 1.78, so that's pretty close. Negative 1.79 units. When I look up here and we want one tail, yeah, because it's only negative 1.79, not 1.79 and positive 1.79. So we just want the one tail. So it looks like 0.05 or 5%. So that is 5% of our area under the curve falls below negative 1.79 units. That means 95% falls above, because remember, the area under the entire curve is 100%. So I guess I should just say that's the 100 minus 5% is equal to our 95%. So now that we've talked about the t distribution and how to use the table, we're ready to do confidence intervals. And again, this is totally analogous to confidence intervals for sample proportions, but we're using a different test statistic. Instead of a z-score, we're using a t-score. And then we have this different formula for standard error. I put my notes for my confidence interval here for your reference. Let's move it up a tiny bit. In our first example, identify a confidence interval for the average mercury content in dolphin muscle using a random sample of 19 dolphins. And this is our data here. That n is equal to 19. We find in our sample the average mercury content is 4.4 with a standard deviation 2.3. The minimum in our sample was 1.7, and the maximum measurement in our sample was 9.2. And before we get carried away, we want to first ask if independence and normality are satisfied. And independence is satisfied because we are told this is a simple random sample of dolphins. The second thing we need to look at is normality. So I have these notes, I copied it off my overview page so you could take a look. In this case, our sample size is less than 30. So we want to know that we're normally distributed, and also the other big thing is that there's no particularly extreme outliers. So if our mean is 4.4 and our standard deviation is 2.3, I would calculate 3 standard deviations, add it to the mean, subtract it from the mean, and see that our minimum and maximum are within 3 standard deviations. If it is, we don't have any particularly extreme outliers. And in fact, actually, all of our data is within 2.5 standard deviations of the mean. So let's do that calculation. We have x bar, which is 4.4, plus or minus 2.5. Our standard deviation is 2.3. So that means this interval is negative 1.35 and 10.15. And you can see our minimum and maximum are in this interval, which means all of our data is within 2.5 standard deviations of the mean. That means there's no particularly extreme outliers. I'm going to continue this problem by calculating a 95% confidence interval. The first thing I need is the standard error. So the standard error is our standard deviation, 2.3, divided by the square root of n, which is square root of 19. So we get a standard error of 52.8%. That's actually quite large. Now we want to compute a 95 confidence interval. I'm going to start by computing the degrees of freedom using my degrees of freedom formula, which is just n minus 1. So 19 minus 1, 18 is our degrees of freedom. Now to get a 95% confidence interval centered around the mean, that means I have 95% in the middle, then that means because the entire area under the curve is 100%, that means 100 minus 95, that's 5%, is going to be on the two tails, or 5% divided by 2, 2.5% for each one tail. And by symmetry, the other tail is also 2.5. I'm just going to draw this on my curves here that come with my t-distribution chart. So if I want 95% centered around the mean, I want then that means there's a remaining 5% divided between the two tails, because again, the total area under the curve is 100%. If 95 is in the middle, that means 5% is between the two tails, which means each tail is 2.5%. My degrees of freedom was equal to 18, so I'm on this line here. And if one tail is 2.5%, that's 0.025, that means my test statistic is 2.10. You can also use the two tails, right? The two tails is 5%, so two tails here is 5% or 0.05. And you see for 18 degrees of freedom, my test statistic is 2.10. Now using our formula for our confidence interval, that's equal to our x bar plus our test statistic times standard error. So our x bar, our population, our sample mean is 4.4, plus or minus our test statistic is 2.10, and then our standard error we calculated over here is 52.8% or 0.528. So what we get then is between 3.29 and 5.51, which means we are 95% confident the average mercury content is between 3.29 and 5.51 units. Here is another example. The FDA's webpage provides some data on mercury content of fish. Based on a sample of 15 croaker whitefish, a sample mean and standard deviation were computed as the mean is 0.287 and the standard deviation is 0.069 parts per million respectively. The 15 observations range from 0.18 to 0.41 parts per million. We will assume these observations are independent based on the summary statistics of data. And the first question is, do you have any objections to the normality condition of the individual observations? And so this is a small sample, so we want to take a look. One, we're going to assume the data is somewhat normal, and then two, we're going to look for outliers. Here we have n equals 15. Our sample mean is 0.287, sample standard deviation is 0.069, and observations range from 0.18 to 0.41. We're going to look at our sample mean plus or minus 2.5 standard deviations. That's our 0.287 plus or minus 2.5, 0.69. That gives us an interval between 0.1145 and 0.4595. So all observations are within 2.5 standard deviation, so there's really no big outliers. So we can be okay assuming normality. And also, as far as the limit, the central limit theorem goes, we were told the sample data is independent. And the next question, estimate the standard error and identify the degrees of freedom. So using our standard error formula here, we're going to take the sample standard deviation divided by square root of n, which we get 0.0178. And the degrees of freedom is n minus 1, so n is 15 minus 1. That gives us 14 degrees of freedom. Next, we can compute a 90% confidence interval. And I'm just going to compute our data from our previous page. Our sample mean is 0.287, our standard error is 0.0178, and our degrees of freedom is 14. Drawing the picture we want for our 90% confidence interval, that means we want 90% of our data that's centered around our mean, which means since the entire curve has 100%, so 100 minus 90%, that means there's 10% for what's left outside this center part, which means each part, because of symmetry, the 10% divided by 2 is 5% on each tail. So either 10% for the two tails or 5% for the one tail. And now we're ready to look at our chart. We're looking at 14 degrees of freedom, which is on this line here. And we're looking at 10% for two tail or 5% for one tail. And that's right here in this column here. One tail is 5%, two tails is 10%. So then our t-score is 1.76. That means our 90% confidence interval is going to be our mean plus or minus our t-score times our standard error. So 0.287 plus or minus 1.76, and then we plug in our standard error, 0.0178, which gives us an interval between 0.256 and 0.318. Our conclusion then, we are 90% confident the average mercury content of the fish is between 0.256 and 0.318 parts per million. Our last topic is going to be our hypothesis test. I have some notes for hypothesis test here for your reference, and the example is the typical U.S. runner getting faster or slower over time? The average time for all runners to finish the cherry blossom race in 2006 was 93.29 minutes. Determine data using from 100 participants in the 2017 race, whether the runners are getting faster or slower versus there has been no change. The first question, what are the hypotheses? Remember, the null hypothesis is the sort of unexciting news, kind of the things are like nothing to report. So that's sort of that there would be no change. So we're going to use H naught, no change. The average runner time was the same for 2006 and 2017, which makes our HA runner times are changing, meaning for 2017, we're going to expect our mean is going to be different from 93.29. The data comes from a simple random sample of all participants, so the observations are independent. Should we worry about normality? The histogram is shown below. So here, looking at this, how many participants? 100 participants, so we're over 30. So we just really need to look for outliers. And in this case, this looks almost normal-ish, like a normal distribution. There's no outliers. There's nothing way out here on its own. So I've noted here, since n is equal to 100, which is greater than 30, we should only be concerned if there are extreme outliers, but there are no outliers at all, so normality is met. Now we're ready to do the hypothesis test. I left our hypothesis up here. We are also given the sample mean and standard deviation of 100 runners in 2017 are 97.32, so it does look slower, and the standard deviation is 16.98 minutes. So it definitely looks slower, but is that just because we happen to draw a slower sample, or is this a real difference? So we find the test statistic and p-value and make a conclusion. And I'm just going to start by calculating my standard error, which is our standard deviation, 16.9, divided by the square root of n, and I get 1.69. Our degrees of freedom is n minus 1, so that's 100 minus 1, so we have 99 degrees of freedom. Now we need a t-score, and this, remember, we're not doing a confidence interval, we're not looking up area under the curve at this point, but we're going to calculate just like we did when we did z-scores using the normal distribution. We're going to find the difference between our 97.32 and what we have for H naught. And H naught, I should have written this down, says that our mean is equal to 93.29. We'll find the difference, and then we'll figure out what that difference is in standard measured units. So in other words, our t-score is going to be our 97.32 minus our 93.29. Remember, for hypothesis testing, we're going to use our, I guess I could call this mu naught, the mean according to our hypothesis, divided by our standard error. So we're 2.37 standard units above what we're expecting our average for H naught. So the one-tailed table for degrees of freedom equals 99 and a t-score of 2.37 says there is 0.01 or 1% of the data for one tail. So that means on the other side, for t equals negative 2.37, because of symmetry, that's 0.01, which it means in the middle, we have 100 minus 0.01 minus 0.01. That leaves us 99.98% of the data in between the t-score of negative 2.37 and 2.37. I kind of summarized this here. The two tails outside the 2.37 standard errors of the mean accounts for 0.01 on the left, 0.01 on the right, which is 0.02. Now, looking at this in terms of our hypothesis testing, remember we assume H0 in our hypothesis testing. We assume this mean is 93.29. Measurements such as this one here, 97.32, is at 2.37 standard errors above the mean. We only expect measurements like this 0.01 or 1% of the time. So in other words, if our null hypothesis is true and we take a sample, let's say we take a sample 100 times, most of the time we're going to expect something smaller than 2.37. Maybe one time in 100 we might get 2.37. So this is a really unusual sample if the null hypothesis is true. And in fact, it's so unusual we might not want to accept the null hypothesis. In terms of p-value, if we have a p-value of 5% or significance of 5%, then here on our testing, our p-value is 0.02 because actually we're testing whether or not the times are changing, not whether it's higher or lower. So if it's changing, it could either be lower or higher. So in this case, our p-value is 0.02, which is lower than 5%. So we're going to reject H0 and accept HA and say, in this particular case, runner times are changing, and from this sample, it looks like runners were slower on average in 2017. To review what we have covered in this video, we looked at sample means with t-distribution. The idea is that we can model the sample mean with the normal distribution and the t-distribution. And it's a very similar process to modeling a sample proportion p-hat, which we had done in our previous chapter. The t-distribution tends to be more useful than the normal distribution with the sample mean. So the first thing we did was looked at when we can use the sampling distribution to estimate the sample mean. And we use the central limit theorem for the sample mean. So when we collect a sufficiently large sample n of independent observations from the population with mean mu and standard deviation sigma, the sampling distribution of x bar will be nearly normal with the mean x bar equal to our population mean and standard error equal to the standard deviation of the population divided by square root of n, where n is the sample size. And the two things we need when we talk about independent observations, the most common way to satisfy this condition is when the sample is a simple random sample from the population, and essentially if the data comes from a random process analogous to rolling a die or drawing tickets from a hat, this would satisfy independence. And the second thing, we need a sufficiently large sample of n. So when sample sizes are smaller, n is less than 30, we require the sample observations to come from a normally distributed population. We can relax this condition more and more for larger sample sizes n greater than 30, as long as there are no particularly extreme outliers. We use somewhere between 2.5 and 3 standard errors as a measure of being extreme. We took a look at the t-distribution, and as n increases, we see the t-distribution looks more and more normal. So the standard error is dependent on the population standard deviation. However, we rarely know the population standard deviation. Instead, we must estimate it based on the sample standard deviation. Because of this estimate itself is imperfect, we have a small sample. If we have a small sample, we use the t-distribution to fix this problem. So we have the t-distribution, there are a number of curves, and we parameterize the particular t-distribution by something called degrees of freedom, which is equal to n minus 1. N is the sample size. The larger the degrees of freedom, the more closely the distribution approximates the normal model. Next, we calculated confidence intervals for the mean, and that formula we used is x bar is equal to plus or minus our t-statistic, our test statistic, times our standard error being s over square root of n. This test statistic is totally analogous to the z-score that we did for normal curves. And then we finished off by looking at a hypothesis test. So that's it for this video. Thank you for watching.